relationship. That was, just going back a bit, I appreciate now you took handwritten notes from that, because they don't exist as a typed thing yet, because I'd only written that morning, to tell the absolute truth. But you do have a longer handout from notes from George Adigariglu, I think, which goes into rather more gory detail than I did. And I would have said at the time, well, yes, that's kind of the gold-plated version. I gave a rather simpler, I think, well, it was definitely simpler in the sense it was cut down version. So, in that's the kind of bread and butter background terminology notation. Do make sure you get that on board at least, because it does lead to everything else. So, to understand the different definitions of quality, what we mean by that, flow quality and bucket quality, whatever term we use, and the triangular relationship that results in, and so on and so on. So that's fairly straightforward material. Rewriting it to yourself or whatever, I would suggest is probably a wise thing to do. The other main bits of the course, what I did, is basic channel analysis. And in a sense, that's the absolute bread and butter, isn't it, of nuclear fuel. And there are two aspects there. Just be able to derive and use the equations for predicting the temperature, the parabolic temperature profile within the fuel pin. Well, parabolic with a little bit of a log term if there's a central hole, okay, but essentially parabolic. The issues about the semi-empirical, empirical treatment of the temperature drop across the gap, albeit it's not a physical gap. The cladding could well be in mechanical contact pushing against the pellet, but there's still a bit of a temperature jump there because it's obviously pointwise contact of two rough surfaces with a gas filling, and the temperature drop through the cladding, and then the final one, the temperature drop through the boundary layer on the fluid side. So we derived all of that. We worked our way outwards from the centre of the pin, or a boundary condition at the centre of the pin, zero temperature gradient, so there's nowhere for the heat to go by symmetry, even if there is a central hole. Most years, someone at least says, well, the central hole is part of the mechanism for cooling the fuel, and there's some whistling flow of gas up there. Well, plainly there isn't. It's all a sealed thing, so don't say that one, please. So that gives us the radial distribution of temperature within the pellet and the cladding and so on, out into the coolant, where we've got a boundary layer, out into the bulk coolant. And then what is the bulk coolant temperature? Well, that's where we start again and go back to the inlet of the core. Let's say, well, the bulk coolant temperature is simply the... Sorry, is it visible up in level 7 that we aren't up there, if you're not? I mean, I asked something. I've got me hanging around up there wasting time.
I
Apologies.
suggest you be down here.
Yes, okay.
No, it's not.
It's not?
I mean, we were up there, and I had to call someone here to actually...
No, sorry, yeah. I did ask...
I wrote it on the board.
You did write on the board?
Yeah, on board.
Yeah, in the drawing room.
Yeah, okay. Perhaps every 5 minutes you could exercise yourself and run up and fetch. Be kind if you wouldn't mind. Save you being bored by me.
I don't feel needed here.
Yeah, so we need to know what the bulk coolant temperature is at each axial location as we're going up the core, since that forms the temperature from which we've just computed the radial variation into the pin. And we do that simply by saying, well, it comes in at a certain temperature, and by the time it's got to here, we put a certain amount of heat into it. It's no more, no less than that. So we just integrate up the channel, the heat being pumped into the channel from the fuel rod, and we know the axial variation of that, because we'd be given it, or it's a cosine, whichever it may be. We've been deriving that busily in our reactor physics, plainly. And it tends to be a cosine, well, for a cylinder. Well, our simple model gives it a cosine. We've seen in real life it's going to be anything but that. So plainly, in the real world, you do this numerically and integrate numerically up this quite arbitrary axial profile. But for present purposes, we'll generally take it to be a cosine, possibly the chopped cosine associated with the use of a little extrapolation length from the reactor physics. Sorry? Yeah, vertically upwards. So let's go through, and I will have done this before, but I think it's a useful exercise. Let's talk through the temperature variation as we go up the channel, because it's inlet, so minus L over 2 if you like, or inlet goes out, so we've got a channel on its side. And first of all, we'll look here at the Q dot dash of Z. So this is Z along here. And the axial variation of the generation of heat. So what shape is that?
We just told us.
I know. Well, yes. After enough years doing this, that has no relationship to whether or not someone will be able to answer the question correctly. I'm unambitious. I note you said I told you, and you didn't tell me the answer then.
It's because he doesn't know.
Oh, exactly.
He doesn't know.
It's all bluff. Right, something like that, cosine. Yep. Well, that's the wavelength or half wavelength. And if we're talking about the extrapolation length, that would just mean we used a shape corresponding to a slightly longer wavelength that would come out notionally like that, but of course actually still stops there. We don't have any heat generation in that far, so we'd integrate a slightly different function of z, cos pi z over Lx rather than L, but we'd only integrate it nonetheless between the minus L over 2 real and plus L over 2. So that appreciation of the physical common sense what you're doing is important. One thing is simply telling it a shape, and it's a way of getting a function in, and the other is saying I'm actually integrating from the beginning of the pin where heat generation starts to the end. So that appreciation of the distinction is important. So that's roughly the shape we'll have, and then we just say what happens to the plot a graph of some temperatures axially. So this is, say, the inlet coolant temperature. So it starts.
Temperature graph.
Yep, there's going to be temperatures up above there. And so it comes in at one temperature, goes out at another. And roughly how different are those, say for a PWR, those two numbers, inlet and outlet temperature? Just always helps to have a physical idea. Sorry? 30-ish, yeah. Remarkable. Whereas it's an order of magnitude more than that for an AGR. So just quite different behaviours. Okay. So there's the start and the end. What's the shape like? Anyone care to volunteer and come and sketch it and explain it as you go? Yeah. There you go. Yes, he's putting his money where his mouth was. Very, very brave of you. Do talk us through as you do it.
So, the class is being held by you today.
The general shape is, as we should see, an integral of the bottom one. An integral of the cosine is some form of a sine function. So essentially, sketch it, so midpoint would be here. We get a shape of this nature. Now, mathematically, so you have a fixed mass flux of coolant times its heat capacity at the threshold volume. Well, is the same for liquid water, a little different from for gas. Times, if I remember correctly, dt over dz, z being vertical distance up into the core, would equal q prime as a function of z. This is some sort of a cosine function, and on integration we obtain this temperature profile.
It's good, isn't he? Yes.
Will we be asked to do integration between limits to actually work out the total
Oh, crikey.
between two temperatures?
Well, honestly, the answer is I literally don't remember if that's in, but I would be very disappointed if you, how can I phrase this ever so carefully, I'm not so rude, if you couldn't integrate a cosine between, but you can, good. You're just asking that to make me worried.
Well, no.
I mean, you might have to integrate by parts.
See what sort of feeling what your mind says.
In the reactor physics, you might be asked to integrate by parts. So
Oh yeah.
you're okay with that?
Yeah, I'm okay with that now. 2 weeks ago, no. now.
Life would have been easier. I gave you the basic maths you need to know months ago. So
We had the same conversation.
okay. Right. Anyway, that was brilliant. So that's the coolant temperature. Just to emphasise then that physically, and that was great to see the algebra. The slope here depends on the magnitude down here. So if the magnitude of the rate of input of heat is 0 at the end, I know that's in our idealised model, but bear with us. If it's a 0 magnitude of generation of heat, we get locally a 0 slope. So at either end, which the maths bears out as well, it does the same. So that the slope, the rate of change of temperature, proportional to the local axial rating, obviously. So by the same argument, where the rating is highest in the centre, we've got the highest slope. So it does that, and indeed it is a sine or a cosine. It's a trigonometrical function, obviously, just coming from integrating that. So that's the coolant temperature. And then the next one we'll be interested in is the clad temperature. And the clad obviously is going to be hotter than the coolant, more or less everywhere. And it'll be hotter by the amount required to drive that much heat, watts per square metre, through the boundary layer out into the bulk. Because that's the process that's happening. We need a hot metal. Fred stayed, didn't he? Or he just buggered off and left us, didn't he? Just realised. We've got hot metal there, bulk coolant going past, and to get the heat from there to there, what we're dependent on is the process of turbulent eddies and swirl and chunks of cooler fluid being brought into contact with the hotter metal and so on, carrying their enthalpy back into the mid-flow. That's the normal process of convective, turbulent convective heat transfer, and obviously it's very turbulent. So that boundary layer where there's a big change in the temperature, the boundary layer has to be, the delta T across that boundary layer has to be big enough to drive that amount of heat. And remember, this is a fixed heat flux device. It's very different from, say, if the fuel rod instead was a tube with hot oil in it, conveying heat to some coolant going past it. That might be more like a fixed temperature type device. Okay. So here, the temperature of the metal will rise to whatever it needs to rise to be able to drive that heat from its metal surface out into the bulk. And the size of that rise, that will be dependent, or we'll characterise that using a heat transfer coefficient, of course, which is simply expressed as watts per square metre per degree. That just tells us the size of the delta T to get a watt per square metre across it. So the metal then will be hotter than the coolant. Here it's hotter by an amount 0 because the rate at which we're driving heat into it is 0. Here it will be hotter by a bigger amount because we're driving in heat more there. So it's a very small one, isn't it? So we'll have a height above there, which rises something like that. Running out of. Don't be offended, I'm just going to redraw the sketch. It's going to make my life a little bit easier to draw it. Okay, so the cladding, where we put, tempted to draw that so that broadly those, it's as if we just lifted the one curve and placed it and folded it over the top of the other one. So at the centre, for example, we've got the underlying coolant bulk temperature rising at its fastest, and we're adding to it a nearly uniform biggest amount of boundary layer delta T. So, take that there. We inevitably end up with the highest point of that temperature somewhere a little bit to the right of or above the axial midplane. Now that's, we get at that, we do the integral up there to get the temperature of the bulk coolant, and then the temperature of the cladding, of course, is that bulk plus the boundary layer delta T, and the boundary layer, I'm not going to go through the algebra on the board, you've got all that in the notes there. The boundary layer delta T, of course, is just the proportional to the local rating, so that's proportional to the cosine term as we go on. So that gives us a relationship for coolant cladding temperature versus axial position. And then the last thing we did on that particular thing was to say, well, what we mostly want to know, obviously from an engineering and safety point of view, design is where is it hottest and how hot is it? So having got that expression for the axial variation, we can differentiate it to see where is it maximum, which finds us this Z location here, which is typically about 60% of the way up. It varies obviously with conditions. And then knowing where it is hottest, you could put that Z value into the expression for how hot it is and work out how hot it is at that hottest location, which is typically, that's a kind of bread and butter question of the sort you'll have seen in previous ones. Almost certainly there will be something on channel analysis. I can't remember whether it focuses on the within pin or within the channel, but that tends to be an area every year that there will be something on that because it is the bread and butter of the okay, I didn't really want to talk non-stop. You're probably very happy with that as well. So what would be useful things to talk about further? Or more specific questions? Exam questions? Well,
Not this year's exam question.
Oh, all right.
Well, that'd be nice, but you know, I didn't think you'd be offering that. Just some past exam. Maybe on something on this slide.
yeah. Yes, I confess I don't have worked solutions to Jeff's exam questions, but you should know those are, Jeff actually releases the worked solutions to his questions, which I don't, but he's obviously a kinder, more user-friendly person. And are you aware, just quick, are people aware those are available?
No.
Oh, they're in Kemenge people. Who's from Kemenge in the room? Must be some, yeah. They're in your library, aren't they? I think they are still on bits of paper as opposed to in some sense electronically, but things may have moved in the last couple of years. So there aren't many things still on paper, but I think some of Jeff's still is. So yeah, if you haven't found those, I imagine they would be a useful resource to help your revision. So how, I'm rather out of this, if you ask Kemenge folk, do you know where the Kemenge library is? I don't. If you can help your fellow students. And how would you find them?
We'll have to ask our might just ask Jeff.
Jeff is not really, Jeff is ill at the moment. I mean, I spoke to him yesterday, but he's out of circulation. He's seriously ill. What I guess would be really helpful if someone from Kemenge today, at the end of today's activities, were to go over to the Kemenge library with whoever else was interested, find out where these things are, then the information at least can then propagate amongst the groups, because I hadn't realised that was less known to. Yes, I haven't sort of intruded into that end of things because it's like it's Jeff's course and it's how he sort of has done things for decades. But yes, I mean, if you can sort that out and are happy to do it plainly, I'm delighted. But it's not for me to. Yeah. So if you can help find where these things are, because that's I wasn't aware that wasn't known. That may actually account for some of the difficulties that we've had where different groups of students have found the course difficult to differing degrees, and it may be that one lot has had access to things like that and the other hasn't, which plainly isn't going to help. So, yeah, do what you can. I appreciate it's the last day of term, but...
so we must find them today, that's what he means.
Yeah, exactly.
Find them today.
Bad luck.
Lost forever.
You're going to get lynched.
No time, pheasant.
Yes.
They're definitely not online, so you're saying they must be on paper.
Well, I know Jeff makes them available because I've always been mildly disapproving of that because I don't think it's a good thing, but I mean that's just different choices and that's fine, he does. All these horribly obscure things he does about critical choke flow of two-phase steam through nozzles and things, which I never understand anyway. So it's just as well he makes them available.
Because there is no Clement library, so I don't know where we will find those pages.
There used to be, but they're changing it now. So
I'm gonna Google
try
it.
then.
When we
Must be.
during one of the pauses this morning, I'll try and phone Jeff at home. I mean, he was in his sick bed yesterday when I spoke to him, so I'm a bit hesitant. But I'll see if I can get hold of him, ask him what the process would be for getting hold of those. But yeah, plainly they should be made available because that is the expectation, and they have been. So I'll really try and make sure that does happen. Yeah. Okay, I'll call him here in the morning. Right, so that probably is the best way to dispose of all of that tranche of the course, because if you've got the previous exam papers, solutions and the notes, probably that together is going to be sort of sufficient. There was, someone said, could I do some worked examples? I could, for example, well, I don't have those for Jeff's, because that's very much was his part. I've got worked solutions to all of my questions from previous exam papers. So if going through some of those would be helpful. I don't like to issue them, but I'm very happy to go through them and people make notes. So if that would be useful.
So I don't know. We've been speaking about this last couple of notes. This session we're doing now.
Yeah.
In theory, we're supposed to start reactive physics at 9. But I'm assuming it's another revision class, is it, type of thing?
Yes.
So there was discussion that maybe we could do 2 hours of each, if possible.
Yeah, I'm very flexible to whatever folks here prefer. Sorry?
True.
Yeah. Well, come 9 o'clock, we can sort of ask the class then and decide how to go forwards. I guess that's because other people may arrive, I guess, all raring to go on reactive physics.
No, I can do some of the obscure things like derive this expression for the critical temperature versus
Oh, I'm very glad for you.
station temperature and such things.
You can do that, can you?
Well, some of them.
Well, I'm very pleased for you. I won't say I wish I could, because I'm studiously avoided.
Well, I sadly have to process them all.
He's looking forward to marking your exam.
You know there are going to be corrections. There are going to be corrections in the paper.
I should subcontract the marking to you. I think it's better.
Yeah, you.
Richard, I think I'd like that. Subcontracting my copies to you. I'll tell you that after.
Nothing online about this chemical engineering library. Secret location chemical engineering library.
I found everything, so I'm Spain after that. So far. Like every week we got lectures like this. Most of them were I found C, I found 18. Basically into material. I had to undo all this paper.
People climbing up the wall, throwing the exam answers through the window. Yeah.
What if we had it on the 7th floor?
You see the people climbing
Yeah,
up?
that was only like the second the single phase, whatever.
Look at that up there.
That man just finished there.
I'll
Yours has page 7. Does it finish at page 7? You have it.
that's a typical Jeff type one. I wasn't proposing to go through that now. You'll now realise why I wouldn't.
Yes.
Again, those are the ones where we will get the solutions to those. Go down. Yeah, okay, that's the kind of thing I started off the morning saying, that the basic, simple stuff about the bread and butter terminology, notation and concepts of two-phase flow and how the ideas of enthalpy and quality and how they are related to whether or not, for example, there is slip between the phases, to the distinctions between how we define them, matter only when there is slip, and so on and so on. And that's just an important basic bread and butter to be clear about, because it underlies everything you'll need to do about the two-phase flow and maybe eventually using correlations and so on. So that's a typical Jeff one. Question 2, well that's the one we started. Okay, derive from first principles an expression for the radial temperature distribution in a pin such as an AGR or PWR. Well, that's where we started. So first principles, what would your starting point for that be? What would you take first principles to mean there?
Statement.
Of what?
A written statement.
Yes, a written statement. It is paper we give you, so no, yeah. But what would your statement be about? Heat balance, yeah, a conservation statement. Yeah, absolutely. So, so what might be a conservation statement in a solid with heat generation in steady? I think it says steady, I'm sure. I don't know, it says steady, I guess, but I wouldn't mind either way. So what would be the
amount of heat generated within a volume equals the amount of heat transferred through the surface of the volume?
Yeah, absolutely. Yeah. Sort of what comes in, what must go out is something of that sort, yeah. Locally at a point, it would be that, just you'd say that the rate of generation at the point must equal the rate of flow away from the point with or without any rho Cp dt by dt if there's actually any change in the stored energy at that point. It doesn't actually say steady, so we could use either then, I guess. That would be fine. So something like div of Q, divergence of Q would equal the local volumetric rate of heat generation. I know I've had a discussion with one or two of you, just this very helpful notation of single primes, 2 primes and 3 primes to indicate the dimensionality of the quantity we're talking about. So Q dot single prime we used over there to refer to heat generation per unit length of our pin. Heat flow through the boundary layer, we'd be talking about heat flow per unit area, so Q dot double primed, and here we're talking about heat generation per unit volume, so Q dot treble primed. It's very simple and very compact, helpful notation. So that would be our statement, and then that just becomes an equation, of course, because we need a constitutive law to, well, we'd have a rho Cp dt by dt, so we've got temperature and heat flow, so we'd introduce a constitutive law to get rid of one of those, and that, of course, is Fourier's law. Q is K grad T. So we come up with a K del squared T. I'll probably drop a sign somewhere, but not too fussed. Okay, so those two together would give us the differential equation that we would solve. And then you'd say, well, in the cylindrical geometry of the fuel pin, the natural coordinate system to use would be cylindrical with symmetry and so on and so on. So you just pick up the cylindrical Laplacian that you're now very familiar with from the reactor physics as well, and write down the equation that you'd need to solve, and then apply some boundary conditions. Just basically, that's exactly the derivation you have in the notes, fine. So table 2, we'll have given you down at the bottom of the page. There we go. Quantity there, so exactly the same kind of thing as you had in the problem sheets. So derive the equations. It really sounds trivial, but like this, you derive the equation, then you just put the numbers in. Obviously, that is literally what you're doing. We've been giving you heat transfer coefficient, not asking you there to compute it from the flow conditions. Okay, so compute the maximum fuel temperature. This was, in this, I wrote this one out because going back a bit, extended to allow for a thin layer of low conductivity crud on the cladding outer surface. Okay, so just like we had, effectively that's like having a second layer of cladding. Exactly the same. So we just treat it as if there was another cladding layer, perhaps have a different thermal conductivity obviously, but otherwise exactly the same. Exactly the same way as we did to take the cladding into account. And then, again, this asks you to go on and say, well, during life, the gap conductance changed. And why might the gap conductance change during life? Yes, that's one possible reason, absolutely. Others? Sorry? Fission product release. Yeah. And how would that affect it? I mean, I'm not disagreeing, but just can you expand?
All the fission products have different conductivities themselves, so
Yeah.
you have to make sure that with the helium and the gap.
Gaseous, which fission products though?
It would be gaseous.
Yeah. So gaseous fission products that get released from the fuel, and the main ones are which? Main gaseous? Krypton and xenon. Yeah. Noble gases, so they don't form chemical compounds and get trapped in the fuel in the same way, so they sit around initially as individual atoms, so they form, migrate and diffuse. There's a kind of equilibrium solid solution of atoms. Some of them meet together as they drift around and migrate and diffuse through the solid. And when two gas atoms meet, I guess that's what we define as a bubble. As more gather together, you form little bubbles within the solid matrix. Bubbles at enormously high pressure, because they're trapped by the surface tension of the solid. Solids have surface tension just like liquids. So whatever the surface tension is, there's a 1/r dependence of the pressure that is formed by that surface tension. So you get gigapascal pressure bubbles trapped as small bubbles within the lattice. So very, very small high pressure bubbles that migrate as bubbles then. And there's still some dispute over the mechanisms that causes bubbles to migrate. Preferential evaporation off the hot side of the solid and deposition onto the cold side, so the net result is the bubble moves, for example. There's various reasons they can move because of stress fields. As two bubbles approach, the stress field around is such that there is a relaxation of stress if the bubbles get closer, so that provides a driving force to cause bubbles to move. Anyway, they do move, migrate, they coalesce and eventually get quite big or get to a grain boundary, and the gas finds its way out. And krypton and xenon then begin to pollute the gas that was used originally as the fill gas when the pen was pressurised around the pellets. So you fill it full of pellets, evacuate it, squirt in some helium, that's a good high conductivity gas, and that's fine. But over life that helium gets diluted with krypton and xenon, and that reduces the gap conductance, which directly raises the pellet temperature, which of course is the bad thing. So you want to know about that and you have to make some estimates. So there we're told the gap conductance had changed to that from whatever it was in the table below. In addition, the crud layer, and we go over the conductivity there, 5 watts per metre per degree, say compared to stainless, which is about 30 or so relatively low conductivity. And it asks you then to compute the new maximum fuel temperature. And of course that's exactly the kind of assessment you'd need to do as part of your safety case. It's one thing to design everything when it's clean and new, but you have to be able to convince the regulator and yourself that during life, up until the point when you take it out, it'll all still be okay. Oh, and the final one indeed, we just discussed that, yes, suggests why the gap conductance might have changed. So again, I think perfectly sort of straightforward, that's the intention, bread and butter kind of question. And if you've done the problem sheets, there shouldn't be any, a little bit of novelty there, you might say, with the crud layer.
So is that what you mean by a constitutive relationship?
Oh, that was, this is
but what does it mean?
A closure relationship or a constitutive relationship. It's Hooke's law. Sigma equals Young's modulus times strain. That would be a constitutive relationship. Or shear stress is some viscosity times du by dy for a fluid flow. That's that's a constitutive. It's telling us something about the behaviour of a material, broadly, is what it means.
Expressing something in terms of...
It's a closure law, that it's something bringing the material behaviour in that's needed to help us understand, to help us go from just a pure conservation statement, typically, to a useful thing we can solve. I think pretty much every bit of analysis we do starts with a conservation statement, followed by some closure law, which is generally a constitutive relation. Electricity, yeah, but saying the electromagnetism, the same relationship between B and H and E and D and things of that sort.
So it's a closure.
Yeah, it's a closure, generally bringing in some physical, some observation of the physical real world, typically approximate, or commonly, but everything approximate. You could argue that the conservation statement is by definition exact because you're just stating it. You know, we're asserting mass is conserved, so that perhaps that isn't perfect. You know, Einstein came and sorted that one, but subject to keeping well enough away from those conditions, it's a pretty much an exact statement, but we'll need something. Okay, so that's very much the in the spirit there. So, I mean, I have here the worked solution of that, but it really is only what you've had in the lecture notes, so there's not a great deal, honestly. A lot of it is probably copied and pasted from the notes. So that's you'll recognise that. I don't think there's much point in going through that, you've got it already. So that's the equation again. It looks a lot, but it's in your notes, it's just slowly arrived at. Photograph on the screen. It's high tech. So where we had a term for the cladding there, which follows down, we've just got an identical term that pops straight in for the crud. It's just an extra thermal resistance featuring in exactly the same way. So perfectly straightforward. If you understood how the cladding featured and how it came and how it comes into that overall expression, just an obvious write the answer down to say, well, there's an extra layer, it will have exactly the same form.
So in the exam we can say that rather than derive it again from the beginning.
Oh yeah, if someone had said and justified it, well, you know, you could do the algebra again, or you can say, well, it's going to be exactly the same. Yes, either is fine, because what you're looking is to see, does this chap know, or person, know what he's doing? I'm sorry. So just make that clear, okay, and then it's fine.
So the last term there was on the syllabus there was supposed to be a lecture, the very last lecture on crud formation, but for some reason I don't think it would happen. Is it?
No, that was a complete cock-up. I knew I was lecturing, this is the truth, I knew I was lecturing the last lecture of the course, and I hadn't realised that Chem-Eng had scheduled the course to be a week shorter.
Oh, right.
So I got it in my diary for the last week of term, and I think the course finished the week before the last of term, didn't it? I was completely thrown by that.
Does that mean that crud formation is not? Because you didn't
Well,
lecture
it
so
was
much?
very, crud, I was relaxed about it because crud is one of the, a bit like the external speakers.
Yeah.
It's something we put in, don't laugh at this, because we think you'll find it interesting and valuable. It's not something that I would lecture. It is, I can spend 10 minutes and tell you what it's about very quickly, because I think it's fascinating, but then we're sad people. Crud forms, it arose from some research we did for National Nuclear Lab at Harwell, I think, and actually, if anyone's interested, they're wanting to sponsor some more in starting now, so we've got another, I'm looking for a PhD student to take this work forward. So, what you observe, here's the cladding, and then here's the fuel pellets down here, so cladding, so this would be like of order 0.5 millimetre or 1 millimetre, and you get a layer of crud formed on the top, sort of messy, looks like kettle scale, and what you actually see, if you look at it, I won't go into the lecture now, it'll take too long, but looking at the top of it, you see little holes like pock marks. It's a little bit like if anyone has ever cooked porridge, and it partly sits steaming on the stove, and you get little like steam holes come up, like popping. And what it is little sort of chimneys. They go all the way down through the crud, down to the metal. So the picture we should have then is water flowing past, and 50 micron or so, like half a millimetre. It varies from a tenth to a millimetre. Thin layer of crud, and lots of these tiny holes that go down to the bottom. And the crud is porous, a bit like kettle scale or chalk or something. And the work, so we go through and just show you the equations, just to kind of give you an example of how, you know, kind of the approach to things, conservation laws and constitutive relations, which is exactly the same again, gets applied. But what happens practically is that boron in the coolant, well, we know now why boron is there, soaks into the crud and gets concentrated in the crud, and you end up at regions where there is crud with a lot of boron, and that lowers the local flux. So you get what's known as axial offset anomaly, or crud-induced power shift, because you get a lower neutron flux in regions where you've got this boron that's hidden itself out in the crud. So understanding where it goes is a problem. In plants that get affected by it, they can have to derate themselves, because they lose that local power, and you can't just jack the overall power up to compensate, because you'll come up against some other limit. So it's not uncommon for a plant to be derated by several percent, which doesn't sound a lot, of course, until you realise, well, if you're selling a gigawatt of electricity, several percent pays for quite a hell of a lot of research and studies to see why is this happening and what can we do about it. So it's surprisingly important. So what happens, it's thought, is that water soaks into here, gets down this hotter region where the metal is very hot, and it actually then evaporates from these chimneys. So you get little bubbles, and then they condense very quickly. You get very hot region down here of the water flowing in. And as the water flows in and then evaporates, it's bringing in, excuse me, whatever is dissolved in it, but that dissolved stuff doesn't evaporate with the water. A tiny bit does, but yeah, big heavy dissolved ionic stuff stays there. So what you actually end up doing is building up, whereas you have very low, fairly low concentrations of nickel and iron and all the muck that's in there off the heat exchangers and so on, it builds up to quite high concentrations in these regions, and pi meaning 10 times or more the concentration out in the free stream. But it's got nowhere to go, so what you build up high concentrations that form an equilibrium because they start to diffuse backwards down that concentration gradient. But the water that's boiling down here is actually boiling in a very, very concentrated solution of whatever. And of course, any chemical engineers will know, if you have highly concentrated solutions of stuff, you're going to change the boiling point quite significantly. So you get a positive feedback that you get a lot hotter temperatures here than you might have thought, because the concentration of all these dissolved solids is so high. But that in turn affects the temperature distribution through the crud, it affects how the heat is getting conducted. Because the heat then, it turns out, coming in more or less uniformly from the pellets below, you end up actually having a very big fraction of the heat coming into just this bit down at the base of the chimney. So it comes in and sort of turns sharp here, and you end up with almost no heat being transferred from there, and almost all of the heat from that whole region turning into vaporization of the water down in the bottom of those chimneys. So it's actually an interesting coupled problem of the flow of the water, the flow, the advection and back diffusion of the dissolved solids, of the dissolved species, beg your pardon, and the heat conduction problem. So it's actually three coupled partial differential equations that all interact to each other in a nicely non-linear sense. But we were able to show actually the total mechanism of heat transfer more or less ceases to be convective heat transfer off the top surface. It's actually a really good way of getting heat off, because we get this boiling process, albeit with pretty hot clad, because we've got very high temperatures under there.
Essentially introducing a large number of nucleation sites.
That is one interesting way you can think of it like that. Yes, it sort of helps. And there are actually commercial manufacturers of heat exchange equipment where you can buy tubes coated with stuff not unlike crud. designed to engineer this kind of local boiling and wick boiling is the phrase. A wick, as a bit like the wick of a candle, where it soaks up the liquid and then it vaporizes and it burns at the tip. So it's the soaking in and vaporizing process that a wick does for you in a candle is what's happening in the crud there. So anyway, so the lecture you missed was me spending 40 minutes going through the algebra a little bit. I hope, for fun, it's never really going to be a hard-nosed part of an exam question, because it wouldn't be fair, but it was... So if anyone is interested, we're just looking to get someone to extend this, because it's more complicated than that, because actually there's lots and lots of dissolved stuff within the coolant, and when you bring it in at very high temperatures, much higher than it's normally used to, like 10 or 20 Celsius, which from a chemical reaction, roughly double rates for every 10 degrees or thereabout, the chemistry of what's going on becomes quite different. And the Harwell folk we interact with, they're these sort of inorganic chemists, probably the best in the world on coolant chemistry and related things. And they involved us to sort of do the mathematical modelling side of this, so we've got a project to take that forward, adding much more depth into the chemistry treatment, into the computational model. Anyway, that's what that was about, or the background of that. That was a lecture that, I'm afraid, just through the timetabling cock-up, got missed. Okay, and that was just me doing the work solution. Okay, is that we are at time. Shall I do another paper on thermohydraulics and then ask the class about where to go from there, because it's still 5 to 9, I think. Yeah. Okay.
Do we want to do one of those critical flow ones?
Do you want to do one of those? Not as much do I want to. Honestly, I don't think I could. I'll be absolutely honest. It's not a subject that I've ever warmed to.
I could probably help you.
Bloody hell, it's an algebraic sort of torture.
Yuri might do that?
Yuri might do that, but maybe I think the highest value I did there will be to spend the corresponding time to get access to the word solution. It's not difficult. I mean, I have done it in the past. It just has never quite been something I've warmed to. So I leave that very much to you. If we'll come back next year and take the course, we'll probably drop it. So that was 2009. Okay, again, this was the next year, but really it's very much intended to be this kind of straightforward bread and butter stuff. We had that last one was derive broadly the radial variation, I think, I forget, but this one again, how different can you get? Derive for a bare cylindrical reactor the actual variation of coolant and flat. So, okay, the bare cylindrical reactor, that's the bit that's telling you, because these people have also done reactor physics, for you to know that for a bare cylindrical reactor the axial variation is cosinusoidal. Okay, so that's why that's in there. So we're not telling you it's cosine axially, but you need to use your knowledge of reactor engineering to get that. Axial variation of coolant and clads, I've rubbed it off, but it's what Yuri is doing for us. Again, I've rubbed that off, nothing personal. Over there. And then sketch it, again that's off. And showing typical numerical values, we'll find there, it's a bonus, but yeah. I think, obviously we don't expect you slavishly to learn numbers about reactors, but to have from an engineering point of view, you ought to have a sense that this one it's about 30 and this one it's about 300. I mean, yeah, come on, that's important. Yeah.
What are the exact temperatures in PWR between the inlet and the outlet? Is it 420?
Blimey, it's like asking David Cameron just how many people are on 0 hours contact. I don't know. I'd have to go and look and play with my MATLAB scripts. But yeah, it's a few hundred in an AGR, it's a few tens in a PWR. That's the level of that we're looking to get. And say the centre to edge delta T is 500-ish.
Oh, so you're not actually looking for a number about the inlet temperature?
We just want.
We did learn that. We have learned it.
Well, I'm very pleased if you. I mean, that's great if you quote actual numbers. I mean, but it's really to give a. You need sort of to know where you are in this parameter space. You know, where is the engineer working? Because obviously it's very different conditions. Yeah. Just like the clad delta T. You know, the boundary layer delta T. It's sort of 10 Kelvin, 20 Kelvin for a PWR, and 10 times that for the AGR. Okay, so that was one. Two, the general layout. Well, there's a good copy. General layout of Newswood Power Station. This is a Jeff question, right?
Yeah.
Loop, integral, and pool types. Well, plainly a PWR is pool type. Yeah. Okay. So again, fairly straightforward stuff. Did Jeff do that this year? Sorry, it's hard to see the bit.
I think you did.
She did.
Yeah.
Yeah. Okay. Again, that's straightforward stuff from Jeff's lecture notes. That derivation will be there. So I don't think I'm used to. They'll often say, well, if you're not clear on those things, go and do that.
I've read it the other day.
Okay. This is the operational states. I confess I don't like that kind of thing because it's a bit like, you know, just remembering a list of things. They're just about normal operation, frequent forms, infrequent forms, and so on. But that's terminology I know. Okay, and again, boiling length and so on, and in the CHF type lectures you'll have had all of that, so back straight to the notes. But just the idea is basic, straightforward material envelopes. Okay, those are from Jeff's. So again, the solution to that first one, I just show it is exactly the straightforward derivation. It'll always be a straightforward derivation, then we just an extra little bit like there was the crud in the previous one, or something else, or a numerical as well. So again, that's what we're looking for. Just show that you can, and there's sketching somewhere. That's the sketch we put on the board earlier this morning, giving borders of magnitude and sizes and so on. That with the coolant, clad outer, clad inner, pellet outer, pellet centre. And just to get a sense of the relative size of those differences, of what this enormous delta T radially through the pellet there. That's this big parabolic profile where we started the morning discussing. Okay, right. It's 9:05. Obviously, we should be doing reactor physics now, so I'm very open. I guess if anyone wants reactor physics, we probably ought to do reactor. Who would like reactor physics? Yeah. Okay. So I think we probably should do that, and perhaps at the end of the session, you know, the 11 o'clock time, when it becomes more informal, I can revert to whatever if that suits. Okay. So what's the most useful stuff we can do for you with reactor physics? Sort of worked,
Same again.
task exam paper type things. Okay.
Maybe a bit of theory in there as well.
Yeah, sure. Again,
just tell me as we go the best